Yeah, so Amanda, I think that's what I want to talk about today. So if somebody can hit record to start recording the meeting. I think anyone can do it. I just can't, apparently. Oh, did I press the right buttons? I have no idea. Okay. Sorry, I am trying to sort. Oh, now, okay, that still hasn't frozen. That's good. At least something's working. Can you see my screen? Okay. Well, this is fun. While this is sorting itself out. Okay, I think you can now, hopefully. While this is sorting itself out, so to answer some of these questions. First of all, yes, Amanda, we are going to cover free radical addition of HBr to alkenes. We're about to do that right now. Hopefully you can see my screen now. That's just, okay, my Teams is just completely locked up. Then are the textbook questions in SciComm due the last day of class, the day of the exam? I believe the SciComm is due the day of the exam. If you need an extension, please ask. And please ask well in advance. I can't grant you an extension after the fact. I can grant you an extension before the fact. If the last, as to the textbook questions, they are due the day of the exam. So that answers those questions. And yeah, okay, I'm figure this out. Probably need to uninstall and reinstall Teams. Okay, so last class, I left off with this example. So AIBN, HBr, heat, 80 degrees, what happens? So what we get is this radical formation of AIBN radicals. So we looked at the benzoyl peroxide radical formation last class. I quickly went through this. AIBN, we generate nitrogen gas, which is the driving force for this. It's why this all happens. And we get this highly stabilized radical. And if we think about this radical for a bit, we didn't draw out the cyanide, but if we do, like that's what that is. And this radical not only is tertiary, but it's also in resonance. That dot means a carbon is there. So there was a lone pair on nitrogen, now there's a lone pair and a radical. So it's a very stable radical. The radical is in resonance. The radical is also tertiary. Those are two things that radicals like being. Good. Okay, so we can make this radical, but you know, good radicals are all relative. They're still really reactive because that's kind of how radicals are. Now, if we're thinking about how this radical adds, that was our activation step. We made a radical, but it is not a radical that is involved in propagation. Note what's here is the main component. If I ask this kind of question on an exam, what I'll normally write is I'll write the number of equivalents. I'll say, you know, 0.01 equivalents of AIBN, 1 equivalent of the isoprene, 1 equivalent of the HBr. But whenever you have a radical initiator, assume it's there in very small amounts. It's not involved in propagation. Now, initiation is when we make a radical that is involved in propagation. And so we take the radical, so initiation. We take the radical we made in the activation step. And we target the weakest bond. Because you always target the weakest bond. The weakest bond is HBr. And you have a choice. You can either make an H hydrogen radical or a bromine radical. Again, the bigger the atom, the more stable the radical. I think that's always true. So halogen radicals are actually quite stable in general, whereas other rows aren't. So the radicals on atoms follow the stability rules of anions, negative charges. Now this is just with respect to the identity of the atom. Because as we noted, they like tertiary centers, which is not what negative charge is like. But they like being on halogens, it's much more stable. So if the choice is to be on a hydrogen or be on a bromine, it rather is to be on the bromine. So this radical grabs the hydrogen and releases the bromine. We've now interacted with one of the major components and we have generated a radical that derives from the major components in the reaction mixture, which is initiation. Propagation is when you get the chain reaction going and you generate your product. So in this case, again, we have Br dot. It's going to look for the weakest bond in the system. The weakest bond is HBr. Br dot plus HBr gives you Br dot plus HBr. That doesn't take us anywhere. Good job, Jesse. Notes. Yeah, it's all fucked up. You're both right. It was just one extra thing. Both right. My correction to my correction was all fucked. There we go. Okay. So in this thing, Shimoitsu got in there first. Then, so in this thing, the bromine radical is going to react with the second most stable thing, which is, or second most unstable thing and weakest bond, which is the double bond. Man, it really throws me when I do that. So at this point, the bromine interacts with the double bond, it breaks the double bond. That's the way to draw the arrow. They meet in mid-space. And then we have a choice of where to put the radical. We can put it on the blue dot, or we can put it, you know what, I'm going to make the green carbon or the blue carbon. Where would the radical prefer to be? So Julie asked, what does the sentence say? The The sentence says radicals on atoms track with stability of negative charges with respect to the identity of atom. That does not say identity, does it, at all? So like sulfur versus carbon versus oxygen, all those rules track with anions. Green, green, green. Awesome. You guys are all right. You're 100% on the green. Right. It's the tertiary center. That's where the radical is going to be. So the bromine goes to the other one. It's not that the bromine prefers to go somewhere. It's that the radical prefers to go somewhere. Great. Now you have another radical, and it reacts with the weakest bond in the entire system, which is HBr. And we know we're done propagation because we're back where we started. We can then draw the termination steps. So in the termination steps, we draw all possible combinations of the radicals from the propagation steps. There were two radicals. So there's three ways of putting them together. Sort of head to head, tails to tail, and head to tail. Because tail to head is the same thing as head to tail. So bromine can come together. Again, the complex one that gets everyone excited. And then this one is just going to give us a dibromide. So those are your termination steps. But your product is a thing made in the propagation, not the thing made in the termination. Yeah, green because of hyperconjugation. You're all 100% right. And literally that is all there is to this. We're looking for the really important thing here is this. This is the step that can screw you up. You just need to think more stable radical is formed. That's it. I'm gonna say that's the only tricky spot for this. How is U polymer? Okay, so what does that sentence mean? The one on the top right. I'll talk about that in a second. How is U polymer rotation for this? You wouldn't. This isn't a polymer. You're not getting a polymer. You're getting a single molecule. This is, if we notice what we're making here, this is an anti-Markovnikov addition of HBr. So that top sentence says radicals on atoms track with stability of negative charges. So S minus is more stable than O minus. An S radical is more stable than an oxygen radical. Br minus is more stable than Cl minus. A bromine radical is more stable than a chlorine radical. Iodine minus is more stable than C minus. An iodine radical is more stable than a carbon radical. That's what I mean by that sentence. Any other questions about this question? Drake says, when we have to do polymer notation, when you make a polymer. So this isn't making a polymer. Normally, if you have, so when are you making a polymer? That might be a good follow-up question. You're making a polymer when there's only really one molecule present. Like, we could get a polymer from this if there was no HBr. So if I take exactly the same conditions and I leave off the HBr, actually, I'm going to get something different. Let's do this one. So we're going to get a polymer, but it's not going to be. Okay, let's do a slightly different example, I think. Yeah. I'm trying to think of a good example for. No, we can do the same one. I noticed I have a bit of an issue with this. Okay. Notice there's no HBr here. So we're going to make the Aibn radical. And it's going to look around for something to do. Now, one of the problems with Aibn is that it doesn't tend, it's really, really hindered. And so although this double bond, we've been reacting with really small atoms, it's going to tend to actually make a slightly different choice. And I wish it didn't do this because it makes things confusing. But hopefully you can see why this is a pretty good radical to make. Because you have a resonance structure for it. I went back to the same starting material, Faith. I changed my mind. Yeah, it's the same thing. So the question I got from, so good job, Melitza. You're right, we needed heat. So this asks if you're able to get the same product from doing the anti-Markovnikov addition from alkene chemistry, what is the purpose of radicals? You can't. You can't add HBr using HBr because you get the Markovnikov product. So with water, you had acid and water, and you added to the double bond. And the acid and water, you got the Markovnikov product. You use the mercury, you got the Markovnikov product. You use the boron, the BH3, you got the anti-Markovnikov product. But if you want to add HBr, there's no anti-Markovnikov version of that, except for the radical. So the Markovnikov is just HBr, just reacting with the system, and the anti-Markovnikov is this one. Because in the Markovnikov product, you would have the bromine at this site, because that would have been a more stable carbocation. But here we've got the bromine at the other site. Okay, so this radical then looks for the weakest, this is sort of initiation. This radical then looks for the weakest bond. Now, again, if it tries to do the same kind of chemistry, you get the same product. So what it is going to do now, it's a primary radical, so it's also less hindered than that tertiary one we began with. So I think this is actually just generally preferred. So I always get confused by this. So what I'm actually going to do is I am actually numbering this, and this is not for your benefit. This is because I am getting confused. 1, 2, 3, 4, 5. And we generate that tertiary radical. Actually, in this was a bad example. I wanted to work through this example. Why is it a bad example? Because I'm going to ask what you think the most likely thing. This isn't going to make a polymer. What you think the most likely thing for this radical to attack is. And writing numbers might actually help. Yeah, Alyssa, that's exactly the purpose. I would not ask you this question on an exam because it's got this allelic thing going. But what's your guess onto what this is going to do? Like, we do have more of this. Its own double bond, exactly, Faith. Because you're going to cyclize. Because you can make a 5-membered ring, and look, if you do that, if you close 1 and 5, you're going to get a tertiary radical. 1, 2, 3, 4, 5. I don't love it. It's a 4-membered ring. We might be okay. I can't count. I thought it was a 5-membered ring, but it's because I fucked up. No. It's to 1. It does bind to 1. I'm really. Today is not my day. There we go. So we're going to get that. Now that is probably going to react with another hydrogen on another equivalent of this, which is going to kind of be the propagation step, right? Because if we follow that logic through, oh, look, that is the same as that. So I haven't drawn them in a line, and you don't have to. You can sort of do this kind of thing. And so we're getting a product from a reaction, and we're recovering more starting material, and that's going to go through this thing again and again and again. Hey, you know what? There are days I just can't count. It's a good thing I'm an organic chemist. I have to come up with a budget this afternoon for a few $1 million, and this does not bode well that I can't count. Rounding error of a few 100,000. Okay, let's try something else. So let's do a simple polymerization one because that's what I meant to do, and then I just got distracted with a more complicated example, but a simple example. So that example we just did, if you can follow it, awesome. I promise not to ask you that on a final exam. But this one is completely fair game. So notice that we know that there's only one thing in there. There's only this acrylonitrile. There's no, which is what that thing is called. There's no HBr, there's no HCl, there's no BRBr, there's nothing else. There's just that. And this is when you get polymerizations because there is only one weakest bond. And so we get the Aibn, we generate the Aibn radical. It takes a look around at what this thing's got. There's no hydrogen on any of this thing to do that kind of allylic allylation, the allylic radical thingy that we just saw. It's only got the double bond. It reacts with the double bond. It generates the more stable radical. And that more stable radical looks for the weakest bond around. And in every other case where we were working with the HBr and stuff, you react with the HBr, you generate a bromine radical, which can then go react with double bond. Now again, it's another double bond is the weakest bond around because there is no HBr. And this is where we start getting polymerization. Because the weakest, it just keeps reacting with itself because that's productive. Like it goes somewhere. It's not like HBr plus Br dot gives HBr plus Br dot. This actually is making something new, but it can only react with itself because there is nothing else to react with. And we repeat because there's nothing else for this to react with. So it will just keep reacting with itself. Note that I kind of draw the two carbons of each of the monomers, like this diagonal. The reason I recommend doing that is it makes making your brackets real easy, and everyone likes easy brackets. So the repeating subunit is that. What you want to make sure is your bracket encompasses all the atoms that were present in the starting material if you're making a polymer. So there's 2 carbons in a cyanide group. I guess it's 3 carbons and a nitrogen, but 2 carbons in a cyanide group, 2 carbons and a cyanide group. That's where my bracket is. And that's what we want to be sketching. So when you do, so to Drake's question, when do I use the polymer notation? When you make a polymer. When do you make a polymer? You make a polymer when the radical's got nothing left to do except react with itself, and it's almost always going to be reacting with double bonds. Okay. I want to do one last kind of example like this, just because I think it ties in nicely with how we're thinking about stuff right now. Yeah, I'll leave it like that. I probably should have had that over the arrow, but I put it under for no particular reason. It doesn't matter, but it bothers me. It's completely correct and there will be no marks off and everything will be fine, but it bothers me, so I am changing it. There we go. Now I'm happy. Okay, so in the previous example, what steps were what? So the initiation wasn't covered. This, or the activation wasn't covered. It was making the Aibn. This is the initiation. This is the propagation. I didn't draw termination. For polymerizations, you can kind of skip it. Because like there's a radical here, and I guess we can terminate by probably, no, yes, you can skip it, but you shouldn't. My GAs will look for it because they are legalistic and wonderful human beings. So I should draw the termination. There's no reason why I needed to leave this thing here out of the bracket. I could have put that in a bracket too. I just drew it outside the bracket to be a little bit clearer that it's the end group, but it would have been fine. So Alyssa, you mentioned that carbonyl chemistry was not involved in last year's exam. Will it be included this year? Yes. Yes, it will. That's why those were more lecture-y lectures. It will be included because the curriculum has changed. So I don't know if you've seen Samara's comment. There's no GA hours today, but she's doing some tomorrow at 4 to 5. I'm also doing office hours right after class on Friday. So 2:30 to 3:30. I think I answered the question there because I think Malitza did that before I kind of gave in and said, I am going to draw termination. This is termination. So you can do, I'd accept this as labeling as well. This would be fine. If you labeled it like this, that's full marks. You can draw it the way I've done it, kind of like this vertical tier of these, that's fine. Or you can do this, that's fine. They're both the same thing. What's termination? It's when you get rid of the radicals. We've been talking about that. Got me scared here, Lisa. It's when two radicals come together to make zero radicals. Okay. So last example I want to do is this and iodine chloride. Okay, so first of all, the first thing that jumps out at us is it's not going to be a polymerization. There's two things present. But what is it going to do? So again, halogen-halogen bonds, generally the weakest bonds around. Except, of course, like this, which is why we're adding heat. So we add heat. I know you didn't mean it like that. It's just the. Okay, it's good. We're cool. We're cool. So the activation, we're going to make the benzoyl peroxide and do this thing with that. I've done that before. I'm not going to draw it again, but we get the phenyl radical. You can equally draw it as that. Or if you're feeling cool, you can draw a phenyl ring as a circle on the inside of a hexagon. It means three double bonds. Those all mean the same thing. Anyways, we got that. Initiation. What's the weakest bond in our system? Other than a benzoyl peroxide, which we've already dealt with. Perfect, Faith. Thank you. Yep. Always these halogen-halogen bonds are bad. The halogen-hydrogen bonds are bad. Noticing a trend here, right? Halogens attached to things that, you know what, halogen carbon bonds are okay. But halogens attached to basically anything else sucks. Okay. Next question. If this is going to react with this bond, which radical are we going to make? Are we going to make an iodine radical or a chlorine radical? Perfect, Samantha. Iodine is larger. Iodine stabilizes is the better radical. So we're going to make a phenylchlorine bond. And we're going to get an iodine radical. Now that arrow coming from the middle of the iodine chlorine bond doesn't tell us anything. So I need to make sure I draw the second arrow saying, hey, the other electron is going on to iodine. which means that chlorine and phenyl make a bond. So you make a little bit of chlorobenzene and an iodine radical. Okay, now that looks for the weakest bond available, which is ICl, which would not be productive. So we move on to our propagation step. So the second weakest bond available is the double bond. I guess by convention I should draw the radical first. It doesn't matter. So again, where am I going to put the radical on the carbon? Is it going to be on the blue or the yellow carbon? And this is why I don't know why they bother giving us yellow. Perfect, Jeanette. Right, it's the secondary, the other one's primary. It's a clear and easy solution. Get that. Now that looks for the weakest bond. And we know it's going to break it the same way we broke it already. I'm going to get that product. Yeah, Matt, so Madison's saying, so can you repeat why we react with the double bond instead of ICl? Exactly. It can react with ICl, but if iodine reacts with ICl, iodine grabs the chlorine, releasing an iodine radical. So iodine radical plus ICl gives you iodine radical plus ICl. So that's not particularly useful. This, well, let's think about this. We've added ICl to a double bond. Now, what if I try and do that ionically? By ionically, I mean no radicals. I want to highlight some of the complexities of this stuff. Do I attack the iodine or the chlorine? No radicals. So remember, which way is the bond polarized? Yeah, so the phenyl radical came when we talked about decomposition of the benzoyl peroxide. So it is. So you get that as an intermediate from the oxygen-oxygen bond breaking, and then that decomposes to make carbon dioxide and a phenyl radical. So that's where the phenyl radical comes from. I like how you phrase that, Malitza. It really is clear how you're thinking. Chlorine more electronegative, so it does not get attacked. You're absolutely right. So you attack the iodine because the chlorine is more electronegative. So the iodine is slightly positive, the chlorine is slightly negative. And so when we follow that through, we're going to get that species. And so where would I expect the chlorine to attack? Green or orange? So iosite. The I minus is more stable than Cl minus. But when you have iodine attached to chlorine, the I is more positive than a chlorine because the chlorine is pulling the electrons towards it because of its electronegativity. It's a very subtle difference. Iodine's a better leaving group. I minus is more stable. But when you have iodine attached to chlorine, chlorine is pulling the electrons towards it because it's more electronegative. And so one of these is kind of like the stability of the electrons on a thing once you've made it versus the tug of war between the atoms. I like those of you who are going with green because it's the secondary center. It'll have a bigger density of the positive charge. More of the positive charge is going to be at the secondary carbon than at the primary carbon. So if you'll note, what we get is we get the same product either way, whether we do this ionically or through radicals. It doesn't matter. You get the same thing in this case. That's different than when we did the HCl thing. And it's because if we think about it, with the HCl thing, we added we generate the same radical versus the same carbocation, but we add, when we do it ionically, we add hydrogen first. When we do it radically, we add the halogen first. Whereas here, the opposite happens. Because of the way this works, we add the iodine first as a radical, we add the iodine first as a carbocation, and my brain just hit a wall. The carbocation and the anion are stabilized by this. The carbocation and the radical are stabilized by the same things in this case. It's hyperconjugation. If there was a resonance thing going on, it might stabilize the radical and not the carbocation. So we would need to consider that. But there is no resonance. It's just hyperconjugation. The radical and the carbocations are stabilized by the same thing. We add the same partner first, we're going to get the same product. So just because this mechanism is the radical mechanism is technically an anti-Markovnikov mechanism, it does not involve a carbocation. It gives you the same product as the Markovnikov mechanism. And that's tricky. I'm going to leave me no think straight. So I'm going to leave us with a practice problem for talking about on Friday. And this is getting back to Madison. Can we talk about retrosynthesis today? Apparently not, but we can leave a question for Friday and we can talk about retrosynthesis on Friday. So what I want to do is I want you to make this molecule let me check. That's going to be really hard. There, that's very doable now. I want you to make, yeah, well, no, I guess we need the fluorine carbon. This is a retrosynthesis arrow. So equivalent, like just like a normal arrow means goes to, this means comes from. So this comes from that. And what we want to do is figure out how. So what I'm asking you to do is give me a set of, what I could say is provide me, I could ask this question two ways. I could say provide a retrosynthesis from the provided starting material. And any other agent. And I could also say provide a forward synthesis. These are essentially the same question with reagents. So I'm asking you to make this from this. And it's basically, you have all the tools, you've seen all the chemistry. No, there's no teaching on a Friday. If there's a request, I can show up and do so I'm going to try and unpack your question in a second. So we'll take up this question next class, but try and give it a go. This is the risk of sounding really lame. This is the funnest part. You have all the tools. Now we can start making drugs. This is a pretty simple thing. I'm not actually sure our project is any more complicated than our starting material, but you now have the tools to move things around and make molecules out of other molecules. You're going to need to do multiple independent steps, one after the other, to get from there to there. Okay, so there's a couple of questions on this one. So first of all, I'm going to ask Jeanette, answer Jeanette's question. It says I'm planning on teaching on Friday the 10th. There is no class on Friday the 10th. You're absolutely right. The last day of classes is the Wednesday. Wednesday is our last class. I will show up in this time slot on Friday the 10th if people have some questions that they want to talk about. Normally I have a 24-hour blank washout for before an exam, but holy shit, this exam is right before classes end. So I'll be here on the 10th. I'll hold this hour open for people to come talk to me. Okay, Mackenzie asked, the assignment opens Thursday at midnight? Yes. So the assignment opens, I believe, tomorrow at midnight. I might correct myself and say Friday at midnight. I don't know if Samra is on the line still. No, she's left. So I'm just going to be safe, and I'm going to say Friday at midnight because I'm less likely to have a pitchfork revolution coming down to my office. So you'll have Friday, Saturday, Sunday, Monday. You'll close. I'll give you an extra 24 hours for because it doesn't open during a weekday, and I want to make sure that you can do it entirely during a weekday if you so choose, if for any reason you cannot work on Saturdays and Sundays. And so it will open Friday at midnight. You will have Saturday, Sunday, Monday to complete it. On that answers that question. Okay, and I think Stephen and Melitza, I think, asked essentially the same question. I hope. So Melitza phrases, how come we consider the stability of carbocation on I for knowing chlorine is added to phenol, yet we don't consider stability with 3-membered ring? Okay, so we are considering, why are we doing this? Why are we considering the stability of these different things? Okay, so the iodine chloride bond is polarized. If I am a nucleophile, negatively charged, I am attacking the positive thing. If I take a look at iodine chlorine bonds, the chlorine is negative, the iodine is positive. The chlorine is more electronegative. So the I is positive, the chlorine is negative. If I'm a nucleophile, I'm attacking the positive thing. That's why the double bond attacks the iodine, not the chlorine, because the iodine is where the positive charge is. Okay, Now with the radical's not looking for a positive thing. It kind of comes in, and there's the bond, there's the iodine chlorine bond. I don't have my camera on. I can't turn my camera on because my Teams is locked up. But maybe that worked, I have no idea. There's an iodine chlorine bond. The radical kind of comes in down the middle. It sees both the iodine and the chlorine, and it can choose to grab either the iodine or chlorine, and it's going to grab the one which makes the other one more stable. It's not about positive charges in this case. So the phenyl group comes in. It thinks, okay, if I grab a little bit of the chlorine, that generates an I radical. That's okay. If I grab a little bit of the iodine, it generates a chlorine radical. That's not as good. And so it grabs the chlorine to generate the more stable radical. So it's because radical reactions are not ionic reactions. I think that's my answer to your question. So Stephen asked why, so I guess they were different questions. Can you go over why chlorine attacked the green carbon again? So this comes back to when we were talking about all the double bond chemistry. I'm going to just skip a couple slides. And what we need to remember with this is that this is equal to kind of a fast equilibrium between this and that. We've drawn the positive charge on the iodine, but the positive charge is also distributed over both carbons. And now if I'm a chlorine ion atom, I've got a choice. If I grab the iodine, I go back to double bond plus ICl. I go back to my starting materials. Is it possible to do? Yes, but I'm back to my starting materials, then I react again. So what are my other choices? Well, I can either attack this carbon or that carbon. And it's not so much like if I'm thinking about, you're thinking, oh, well, this one's more accessible because it's primary. You're absolutely right. But how much positive charge is on that carbon? It's a primary carbocation. It sucks balls. That is a bad carbocation. It does not exist. This is not a significant contributor. So the chlorine, given the option, attacks the secondary carbon because the secondary carbocation is a fine carbocation. It's not great, but it's so much better than the primary. And my only other option is grabbing the iodine and going back to my starting materials, and that wasn't awesome because I was reactive. So this is the best of a bunch of shitty options. And so that's why we attack that secondary carbon. Okay, Olivia, I'm going to correct that. That clearly is what I said, so I will collect that email. Thank you for letting me know I did that. Yes. Yeah, I'll send out an announcement. Arian, I think she's going to be here tomorrow, she said. She just dropped by a moment ago. Between 4 and 5 p.m. tomorrow. And if not, you can also arrange a call with her. So you can email her directly. The nice thing about the Outlook thing is you can just start typing in somebody's name, and I think she might be the only Samra around. And you can email her directly to talk about that. But if you also have a contesting a grade, email me. This was by far the most frustrating midterm for, I'm sure, all of us you've ever written and that I've ever had to grade. Just, I regret all my choices. Okay. Yeah, have a good day, everybody. I do need to run, so I hope you have a good rest of your day, and I will see you guys Friday. Ciao.